Hey everyone, and welcome back to PrepFusion. I'm Anish, and today we'll be starting the lecture 3 of controllers and compensators. So in this lecture, we'll study about different types of compensators. What is basically compensation means? What does compensation means? Why we do that? And what are the different advantages? And what are the characteristics of different type of compensators? But before going to that, I want to quickly summarize what we learned in the previous lecture. We learned about the controllers. So we learned different types of controller. First one was that simple on-off controller, where there were only two levels. Either it gives some K2 output for a particular error value, or it gives K1 output for a particular for a range of error. Okay, if it is less than this particular value, then it gives K1. If it is more than this, then it gives K2. Okay, these two things you have to keep in mind. Now the example we learned about room heater, this was very simple, and we don't use this because this doesn't ever go to steady state. Okay, that's why we don't use this. Next, we used about the proportional controller. So what is a proportional controller? Basically, just hold on a second, let me check if everything is recording. Yeah, everything is recording. Yeah, so what is a proportional controller? Proportional controller basically gives controller output proportional to its error input. So whatever the error is, that much extent it will get output. Now what was the problem with this? Everything is fine because it is cheap and it is easy and simple to design, but it cannot totally eliminate the error. It can control the error, but it cannot totally eliminate the error. We did one very good example, right? Also, with proportional controller, we can only move through the root locus. We cannot place our poles here and here. It is not possible to place our poles here and here or here and here to change the time domain parameters. Yes, it is possible to change the time domain parameters, but only wherever the root locus of the system will follow, to that path I can change. But if I want to place exactly here and here, no, I can't do that because my root locus doesn't pass through those points. So I won't be able to get my desired performance according to myself. So yeah, that is the drawback of proportional controller. And then we learned why the steady state error can't be zero. So we did a very good example with a hover example. So yes, one thing is for sure, if we change the type of the system, if the system type is changed, then obviously steady state error can be zero. Okay, with proportional controller also. But it's not like proportional controller has made the error zero. It was already zero. If here is like step input is here and this was a type 1 system, then already the error will be zero with or without the proportional controller. Proportional controller can only reduce the error, as we see from here, the formula that we got, and from that explanation. I can't explain again because that explanation is very difficult. Okay, so that we learned that yeah, mathematically the steady state error is depending upon this Kp, but it can't go very high because there is limitation also. Okay, because it may shift the root locus, it may become unstable. Also the system will become very costly because high gain amplifier means more cost. So that will be drawback for this proportional controller. Then I did the mathematical proof. Then we did some key points, and we did the steady state error due to step disturbance. So again, the same thing, same story. It can't totally eliminate the error, but it can reduce the disturbance. Okay, so yeah. Then we learned about PI controller. So the error wasn't going to completely eliminate. So we thought about a new controller, which is a PI controller. So here integral action is also there. Even though the error is constant, then it will accumulate and give more input to the actuator so that it can further reduce the error. So that's what this integral controller does. So we learned about that, but there were few problems with it also. And also we learned about the controller parameter space. So basically it is a space in between our desired region, so where that Ki and Kp value will satisfy, in which I will get my desired performance. Like I want my steady state error to be 0, or I want my steady state error to be this particular value. So this will lie within this particular region. So these are the things. Now we learned about the steady state error with intuition, and we saw that yeah, integral controller is almost making it zero. It's making it zero. Okay, so but there is a problem with integral controller, that it has a actuator saturation problem, that is a wind up problem. So what happens with that? So we learned about like it acts as a low pass filter because integrator itself is a low pass filter only. Okay, but like there is a pole at s equals to 0, that is very important. Okay, that can destabilize the system. So we learned about the wind up phenomena, where initially if the error signal is like positive, low value but positive for a while, then this will only accumulate and this will give more and more input to the actuator, and the actuator may get saturated, so that may damage the actuator. So that is very harmful. So that's why it is very dangerous to use only integral action. Proportional action can also like should be used with this controller. Okay, so yeah, so that's why generally we don't use this PD controller. We use lead and lag compensators because those are the approximations. Okay, because pole at s equals to 0 is very harmful. So then we again did the steady state disturbance. In the same case, it totally reduced the steady state error. Okay, so then we learned about the proportional derivative controller. What was the issue previously? The issue was, yeah, it was the actuator was going too high. Okay, actuator was like input to the actuator was going too high. We don't want that. We don't want that oscillations. We don't want those. We want to reduce the oscillation. So this PD controller helps anticipate those oscillations and further reduces those. So it basically brings a factor of damping in it. But here also we had an issue. What was the issue? Issue was basically, firstly, it is an improper transfer function. It is a non-causal system. Okay, basically the current output of the controller depends on the present and the future input. So that is a non-causal system. So yeah, that is one thing. Then it amplifies like low magnitude high frequency noise. That was also one issue. So these were the issues with that. So we just dealt with each of the issues, how to remove them. We thought about. So we basically use the causal approximation, which will study lead compensators, and that will be helpful for removing this cons of this system, because obviously non-causal system is not realizable, right? So that is the thing. So then reduction, like how does it reduce oscillations, we learned mathematically. I won't like tell you about this here, but this does help in pole placement. This can change the poles, okay, location of the poles. Then this is the main thing that generally is used, PID controller, where all of it is available. So obviously we want everything. So we want to reduce the steady state error, we want to get our desired performance, time domain performance, and like yeah, and P control is there just to stabilize things. So yeah, this is the PID control, but obviously complexity increases because now we have to choose 3 values and within a region, which will be very difficult to choose. Okay, so again, these are the key points. These are the things: complexity, integral derivative, like what does each thing do, we have learned. Then we did few sums regarding this PI controller, how to solve this. Basically these are simple and you can easily solve this. Generally route or root locus, anything you take help of, and you will be able to solve these sums. Okay, PI controller. These terms you have to know: the proportional band and the reset time. So proportional band is dependent on the kp. It was 100 upon kp, and reset time, you just take common of this PI controller, like the ki term, then you will see kp by ki. So this is the tau basically. So tau is equals to by tau reset. Okay, so this is what was given over there, and yeah, this was the answer for this question and we solved it. Okay, now we'll study the types of compensators in this chapter. So basically, what is a compensator? So compensator are approximations of controllers. So obviously we don't use controllers alone, I told you, right? So we mainly use compensators to control our this system, right, which are generally implemented in control systems. So these are actually implemented in the control systems. Controllers are there, but we have to approximate them, because again, you saw, right, something is a non-causal system, or like there is actuator saturation. All those things we don't want. So that's why compensators are there to approximate those, to implement actually in the control systems. Then second point is they also help in phase compensation of the system. What do you mean by phase compensation? We'll slowly studying this lecture, we'll understand what are the different types of compensators. The different types of compensators are lead compensator, lag compensator, lead lag compensator, and lag lead compensator. So mainly we have 4 types of compensators. Now like we'll study each of them one by one. What do you mean by phase compensation? So let's say I have a compensator here and I give it some sinusoid input. Now if this is a LTI system, so if this is a LTI system, then what will happen? Then my this output will be magnitude of the sine Vm times the magnitude of this GC at that particular frequency omega naught. Okay, into, like, this is a signals and systems concept of eigenvalue, so you will learn there, but I am directly writing the result over here. If this is a LTI system, the output will be something like this. Now sine omega naught t plus angle of GC of j omega naught. Okay, so this will be my output. Now here we see, right, there is some phase difference. there is some phase difference between the input and output. The phase difference is angle of angle of GC j omega naught, and here there is 0. So phase difference, there is some phi. Okay, phase difference. Okay, so yeah, this is the phase difference. Now many things depend upon this phase. So this is the phase compensation that I was talking about. So with the phase compensation, what we can do, we can definitely change the phase margin of the system, we can change the stability of the system, also other parameters also we can change. So now I just want to write few things, that if this angle of GC of j omega naught is greater than 0, okay, if it is greater than 0 for any value of omega, then it will provide, for all values of omega, it will provide lag compensation. So just any value, I'm not writing the omega, for whatever range of values of omega, for that range it will give, it is known as the lead compensation, because my angle is positive, so it is leading over the this reference is 0, then angle is positive, so it is leading. So this is the concept of phasor diagram. So lead compensation, okay, lead compensation. Now again the same thing, if this is less than 0, okay, less than 0, then this will provide lag compensation. Okay, so yeah, because it is lagging from the reference, so either it will provide lead compensation or lag compensation. So yeah, again, like if we have, like, for few values of omega this is providing lead, for few values of omega this is providing lag, then it will be called as lag lead compensator, as mentioned here. If for all values of omega it is providing lead compensation only, then it is known as the lead compensator, and same as the lag compensator definition. So generally our compensator transfer function is written like this: Kc times s plus 1 by tau into s plus 1 by alpha tau. Now what is the thing, if my 1 by alpha tau is greater than 1 by tau, 1 by alpha tau is greater than 1 by tau. Now if this is the case, then what is happening? If 1 by alpha tau is greater than 1 by tau, that means, like, let me draw the pole zero diagram. So alpha tau is, so this will be more closer and this will be more further. Okay, so if this is more closer, this is more dominating, so it will be like a lag, it will be like a lag. Okay, but it depends on the alpha itself, so if 1 by alpha tau is greater than 1 by tau, that means the pole is more nearer to the origin than the this 0. So what will happen? This will be more dominant, so it will give more lag, more phase lag. Okay, so what do we get? So obviously I will derive it to you here. It becomes alpha is less than 1. That means if alpha is less than 1, then we'll get lag compensation. Okay, lag. If pole is nearer, we'll get lag compensation, because yeah, this is nearer, so this will contribute more angle than this. So let me just write the angle expression, then you will understand. Tan inverse omega tau minus tan inverse alpha omega tau. Okay, so angle of GC omega. Okay, so this is the case. Okay, so if alpha is less than tau, if alpha is less than 1, then what will happen? This is less than 1, so this will be lesser than this, so angle will be positive. Okay, I made a mistake over here, sorry. Like, this will be for alpha less than 1, this will be lead compensation, lead compensation. So my 1 by alpha tau is greater than 1 by tau. So where is my this okay, sorry, I made a huge blunder, that the pole obviously will, pole location will be like this, the pole will lie here. Okay, for this case I was making a blunder. This is minus 1 by tau because this is small, right? These are the pole locations. This is a 0 location, these are 0 location sz, and this is the pole location sp. So here obviously my pole 0 is here and my pole is here, so obviously this will contribute more angle as this is nearer to the origin, and we can see from here as well. So alpha is less than 1, then this will dominate, hence this will be positive angle, so this will be a lead compensator. Now for the opposite case, you can just do it for yourself. If alpha is greater than 1, then this is a lag compensator. Okay, this is a lag compensator. Now if this is a lag compensator, like, then the pole will be lie here and pole will lie here, then alpha is greater than 1. Okay, as alpha is greater than 1, this will be more near to the origin than this. So yeah, this is the case for these two things. Okay, so I just wanted to mention that when is alpha less than 1, alpha greater than 1, because this will be used in the next phase, next slides. So now let's come to the lead compensation. As I told, right, it adds phase lead to reduce any excessive phase lag associated with the uncompensated system. So basically, if I add some phase, what will happen? The phase margin will increase, phase lag will reduce, phase margin will increase, so that will make my system even more stable, and obviously other parameters will also improve. Okay, so this can also be said as the causal approximation of proportional derivative controller. So this is a causal approximation of proportional derivative controller. Controller. Okay, so this is what we can say. So now what is transfer function? I told you that compensator transfer function will be something like this. Just this alpha will be changed for the lag compensator, that I will explain. So here my alpha has to be, obviously it can't be negative, because the the pole will lie in the right half lane, which you don't want, obviously. So as I told, right, alpha needs to be less than 1. So the range is alpha for alpha is alpha between 0 to 1. So yeah, it can't be less than 0, because can't be, like, pole can't lie on the right hand side. It will make the system unstable, which is obviously we don't want. Like OLT will be unstable, and we don't use those non-minimum phase systems. And tau has to be greater than 0, obviously pole lying on the left hand side, and Kc has to be greater than 0. So, okay, so these are the range. That is why it is less than 1, the reason I explained earlier. So what does this compensator introduce in the system? It introduces a open loop 0 at s equals to minus 1 by tau, and open loop pole at s equals to s equals to 1 by alpha tau. Okay, so s equals to 1 minus 1 by alpha tau. So basically let's draw the pole 0 diagram, as I mentioned, right? So whenever we have a lead compensator, then obviously 0 will lie here and pole will lie here. So this is like a 0 dominating system, because like what we know about the dominant pole concept. So basically whichever is more nearer to the origin will have more effect towards the transient response. But that was for like poles, that was for the poles. But here, as we learned the concept from that whichever is near the origin, that is known as dominating. So that's why generally we tell that it is a 0 dominating system. Lead compensator is a 0 dominating system. So the pole 0 diagram will be something like this. Sigma j omega, and 0 will lie here and pole will lie here. So my 0 will be 1 by alpha tau, and pole will be minus 1 by, sorry, 0 will be 1 by tau and pole will be 1 by alpha tau. Okay, so yeah, this is known as a lead compensation, and for lead compensation is also known as zero dominating system. Lead compensation also known as zero dominating system. Okay, so the control transfer function is this. So if you break it down into two parts, again the magnitude and the angle. So mainly we'll be interested in the angle itself. Magnitude we are not that much interested. So how can we break it down? So here the magnitude gc of j omega can be written as kc into under root. So we can put this whole over a under root, but let's do this here only. Omega, like this will be, if I just multiply with alpha tau, this will be a bit simpler for me. So what I will do is, before doing this, I want to do that, I'm just writing in rough that let's just multiply alpha tau both numerator and denominator. So this will be kc alpha and this will be, so sorry, I'm just multiplying tau with, like taking common tau with this and multiplying alpha tau. Okay, so like this is, I'm taking a common denominator and common denominator here. So the common denominator is tau over here and it is alpha tau over here. So this will become tau s plus 1 and this will become alpha tau s plus 1. Okay, so this is what this is. Now like if I just do the magnitude condition, this will be omega tau square plus 1 and this will be, obviously alpha is outside over here, and this will be omega alpha tau square plus 1. Okay, so yeah, now this is what is the angle condition, like what is the angle value? Angle value is very simple. It is simply, as I wrote there earlier, tan inverse omega tau minus tan inverse alpha omega tau. Obviously alpha is less than 1, so this will be lesser than this one, so obviously it will be always positive. Now what are the corner frequencies for this? So basically the corner frequencies are the poles and zeros. So first we'll get a 0. So corner frequency we'll get a 0 first. So 0 is at s equals to minus 1 by tau. Okay, so we'll get a 0 first, then this is 0. Okay, then we'll get a pole which is at s equals to 1 by alpha tau. Okay, so my corner frequency 1 will be 1 by tau, omega c2 will be 1 by alpha tau. Okay, so yeah, first this will come and then this corner frequency will come. So if you just draw the Bode plot of this one, if you want to draw the Bode plot, right, so magnitude is here, so like DC gain is kc times alpha, and at infinite frequency what is happening, this one will dominate. Okay, if this one dominates, then we have only 1 by alpha over here. So 1 by alpha into kc alpha is kc itself. So as alpha is less than 1, so initially I will have lower gain. So lower gain because initially I have kc alpha gain, then alpha is vanishing, so I have only kc, so it will go up, obviously higher gain. Obviously from the diagram also you can understand. So let's first draw this. Omega, and this is the magnitude of j omega. Okay, c in dBs. Now what will happen? First I have a 1 by tau, and then we have a 1 by alpha tau. Pole is later, we are getting pole at later stage. First we are getting a 0. Okay, so obviously initially my gain was I have a DC gain which is 20 log kc alpha. This is based in, then I got a 0, obviously first corner frequency 1 by tau, I got a 0, so it will go on like this. Then I have a like pole up here, and what is the gain? This is where the slope changes again. So here my slope was plus 20 dB per ticket, I got a pole, so my slope will become 0. So I hope you are recalling your Bode plot concepts. So slope will become 0, so this will be 20 log kc only. This will be higher because alpha is less than 1. Okay, so this is 20 log, sorry, this is 20 dB per decade. Okay, so yeah, these are the poles. Okay, so what about the phase? What are the phase? So the phase will be something like this, that it will be positive for all values of omega, that is for sure. But if we just check one thing, that at omega equals to 0 I am getting 0 phase, at omega equals to infinity this is 90, this is also 90, so I am getting 0 phase again. So it will be positive always because this will always dominate, but it is like starting from 0 going to some certain value high, then again lowering down. So the graph will be like this, that obviously I am not drawing the Bode phase plot approximation, that we don't have time for. So this will be angle GC of j omega. Okay, now how will it look like? It will look something like this, that initially my phase will increase. Okay, initially I will get a 0, my phase will increase, then again it will reach maximum, then it will reduce again. Okay, phi max. So this will be the case. So this is phi m. Okay, and this is this is omega m. This is omega m, and this is the frequency at which my phase is maximum. So this is very important point, we will obviously derive this, but my phase plot will be something like this. If you want to do it with a like the Bode phase plot approximation, what you can do, just simply initially my phase will be 0, then it will increase, then suddenly I will get a effect of pole. Okay, then the effect of 0 will go away, then again I will go to 0, and then it will be like this. So the phase approximation will be something like this. I want to draw the approximation from here itself. Okay, phase approximation like this, and I don't know like what will the maximum point or something, but I can certainly draw the approximation, the Bode phase approximation I'm talking about. So yeah, so it will be something like this. This is the Bode phase approximation. Bode phase approximation. Oh no, like I was in like some call, I turned off the recording and I forgot to press the record button. I'm literally very sorry for this. So yeah, I was telling that what is happening is that if I see for lower frequencies, my gain is kc alpha. Okay, which is lower. Okay, and for higher frequency it is kc. Now I had a question, why is kc important? Why is the controller gain important? Kc, like if kc was equals to 1, then at DC gain, my DC gain would have been what? It would have been something negative in dBs, or in absolute values in decimal scale, we would have got attenuation. Okay, and for low frequencies we are getting attenuation. The compensator is attenuating low frequency components, which we don't want. So as alpha will lie between alpha like less than 1, because 0 to 1, because this is a lead compensator, and for lead compensator my range of alpha is between 0 to 1. Okay, range of alpha is between 0 to 1. So this is about the lead compensator. Now yes, so if kc is 1, I will get attenuation, which I don't want. That's why kc is very important. Kc something higher than alpha or something higher than 1, okay, is very important, so that it doesn't attenuate low frequency components. Okay, so now comes the next thing. Next thing is at what frequency my phase will be maximum. So here we're getting some maximum phase, right? So we want to find that frequency at which my phase is maximum. So how to find that? Basically it will be, we have to write the angle expression and then differentiate that, and then again find the value of omega. So for this case I will do, and for the lag compensator I won't do. That is homework for you. Now my angle is GC of omega equals to tan inverse omega tau, tan inverse omega tau minus tan inverse omega alpha omega tau. Okay, so this is the angle expression. Now obviously I will differentiate this. dd omega angle of gc omega equals to, what is this? This is 1 by 1 plus omega tau square, the differentiation of this. And obviously don't forget this is omega tau, not just simple omega. So obviously we have to differentiate this also, chain rule. So this will be into tau minus 1 plus alpha omega tau whole square, and alpha tau is present over here. Okay, so then obviously this has to be equals to 0. This has to be equal to 0. Then we'll get maximum phase. So if I equate this equals to 0, then I will get alpha tau into 1 plus omega tau whole square equals to tau into 1 plus alpha omega tau whole square. Okay, so now next what happened? Now we can equate for omega. So this is omega m. I just forgot to write, this is omega n. Okay, so this will become alpha tau, just hold on a second, alpha tau plus alpha, okay, tau I can cancel, sorry, tau I can cancel, I forgot that tau can easily get cancelled over here. So I will get this alpha plus alpha omega m tau square equals to 1 plus alpha omega m tau square. Okay, so this is alpha. Now what we can do, we can take the alpha thing common. Okay, so like what we can do is I can take this omega tau square common. So I will take this alpha to this side. So this will be alpha square omega m tau square equals to 1 minus alpha. Okay, so and also there is also a alpha over here already. This is negative and this is alpha omega m tau whole square. Now what I can do, I can take the alpha omega m tau whole square common. So alpha omega m tau whole square, if I take common, this will be 1 minus alpha, and this is also 1 minus alpha. So obviously my omega m square equals to 1 by alpha tau square. So my omega m, the frequency at which I will get maximum phase, will be 1 by tau under root alpha. Okay, so this is a very important relation, and you have to remember this. This is very important because direct question come up from this. Okay, so how can you remember this? So basically what you can do, that this is the, if you observe this correctly, this is the GM of both corner frequencies. GM of corner frequencies. So basically what do you mean by this? So like what is GM? GM is the geometric mean. What are the corner frequencies? Corner frequencies are these two frequencies. So if you multiply this and take the under root, okay, because we have only two elements here, so it is 1 by tau into under root alpha. So yeah, GM of both of them are this, okay, 1 by tau under root alpha. So yeah, this is how you can remember this, that it is a GM of product of those two under root. So I can write this as omega m is equals to omega z into omega p. Okay, so it is the product of these two. So yeah, you can think like that also. So now let's find out what is the maximum phase. We found out the frequency at which the maximum phase is happening. Now let's find out what is the maximum phase. So phi max, let me just put the value of omega n at that equation. Phi m equals to tan inverse omega tau. So omega is now this, tau is here 1 by tau under root alpha into tau minus tan inverse tan inverse alpha omega tau. So this will be 1 by alpha into alpha tau. Okay, so my phi m becomes this tan inverse 1 by under root alpha minus tan inverse under root alpha. Okay, so my phi m, like it is simply tan inverse x minus y. So the formula will be overall tan inverse 1 by under root alpha minus under root alpha 1 into plus 1, because it is simply x into y, 1 plus x into y. So this will become tan inverse 1 minus under root alpha by 2 under root alpha. Okay, so this is the tan inverse thing. Now obviously we can't remember this. How to remember this? So what is this? Base upon hypotenuse, sorry, height upon altitude upon base. So that is what the tan theta is, right? So if tan theta is this, so I can just simply draw a triangle and derive it in simpler terms. So it is height upon base. So the height is what? Height is 1 minus alpha. Okay, so the height is 1 minus alpha. So here this is 1 minus alpha and the base is 2 under root alpha. And what is the hypotenuse? Hypotenuse is 1 minus alpha whole square plus 4 alpha. So it becomes 1 square plus alpha square plus 2 alpha under root. It becomes 1 plus alpha. Okay, 1 plus alpha comes. So this is the phi m basically. So what is the easier term to expression to remember? Obviously everything is like same only, but like we generally write this in terms of sign, because we have 1 plus alpha and 1 minus alpha, and that is more easier for us to recall. If you just remember this triangle, that is also good. So what you do is, what is sine phi m? Sine phi m is height upon opposite upon hypotenuse. So altitude upon hypotenuse, which is 1 minus alpha plus 1 divided by 1 plus alpha. So phi m will be sine inverse 1 minus alpha divided by 1 plus alpha. You can like remember this formula. This is very important formula, or you can simply like just remember this triangle. From there you can derive whatever suitable you find. Okay, to remember it pictorially or just like with the formula itself you can remember. Okay, cos phi m is simple only. That's 2 under root alpha divided by 1 plus phi. I'm not writing it. Okay, so yeah, these are the things that you need to remember. Now how else can we remember this? Now do remember this, that this thing, right, this has to be less than 1 obviously, because this ratio has to be less than 1. So if I put 1 plus alpha above this and 1 minus alpha below this, then this won't be less than 1, this will be more than 1. So how to remember? Like pictorially I showed you how to theoretically remember. So let's say students generally get confused between 1 plus alpha and 1 minus alpha. So if I write this as 1 plus alpha by 1 minus alpha, then if I just take the magnitude of this will be greater than 1, which is not possible. We can't take the sine inverse of greater than 1. So not possible. Now why is this magnitude greater than 1? Because my alpha is less than 1. So if my alpha is less than 1, this denominator is basically something less than 1. Okay, obviously between 0 and 1, and this is what? This is something more than 1. So again, overall it will become something more than 1, which I definitely don't want. So just be careful about that. So yeah, that is how you can remember this if you get confused between the numerator and the denominator. Okay, so yeah, this was one trick that I wanted to tell you. So now basically what is the magnitude of my transfer function of my compensator at that frequency, at the maximum phase. So let me just write the magnitude. G of j omega at omega equals to omega m. Okay, so at omega equals to omega n, it is like the, let me just write the magnitude function over here. Where is the magnitude? Yeah, magnitude is here. Now if you put omega equals to omega m, you will get something like this, that kc into alpha, this is omega m, so it is 1 by tau into under root alpha, so this will be 1 by alpha, and this will be okay, one thing I made a mistake over here, that I wanted to tell you the approximate magnitude, not the exact magnitude. So what we can do is we can simply use the Bode plot. So yeah, this will give me the exact magnitude, but I don't want this. Okay, I want the approximate magnitude. So what I will do is, if you want to remember this, that is fine, but I just want to derive it. You can derive it directly from the Bode magnitude plot also. So how to derive this? So basically this will be some frequency. Okay, so here just let me move this further away. So this will be let's say obviously it will lie between these two, right? Geometric mean means it will lie between these two only, so it will be somewhere around here where phase will be maximum, and this value is 1 by tau into under root alpha. Okay, now how to do this? So what will be the magnitude at this point? What will be the magnitude at this point? So we can use the slope formula again. Okay, slope formula again. So how to use the slope formula? Basically, let me name this point as yb and this as ya. So this is point A. So my value will be simply, let me name this as yb. So slope is what? Slope is plus 20 dB per decade, which is equals to yb minus ya. Ya is 20 log kc alpha divided by log base 10 omega b1 omega a. So what is omega b? Omega b is simply 1 by tau under root alpha, and omega is 1 by tau. Okay, so this was becoming 1 by under root alpha. So 1 1 by under root alpha. So if you multiply with that side, so this will become 20 log base 10, and this is like 1 by under root alpha. I can take it common like this, and this will become under root alpha equals to yb plus, sorry, this is also minus 20 log 10 kc alpha. Okay, so if I just take this on that side, this will be yb equals to 20 log base 10 kc into under root alpha. Okay, so this will be the answer. Now if you want to do this one thing, that it will, we can write this as what? We can write this as if kc is equals to 1, if kc equals to 1, we can write 20 log under root alpha. Okay, and okay, what other thing am I missing here? This will be plus, so this will be under root alpha. Okay, yeah, this is already minus, so that is fine. 20 plus, yeah, this will go there. So this will be something 20 log under root alpha, and sorry, there will be 20 also here, right? Kc is equal to, there will be 20 also here, and this is equals to 10 log of alpha. Now what we know that our alpha is less than 1. So if alpha is less than 1, then obviously we're getting some attenuation. So alpha is less than 1, anyways it is less than 10 anyway, so anyways we'll get some attenuation. Alpha is less than 1, so what will happen, we'll get some attenuation. So attenuation if kc is 1. So obviously we don't want that, sorry. Yeah, sorry for the interruption, actually someone came at the door. So yeah, this is the attenuation basically. So now let's read few key points. So the first key point is causal approximation of PD controller is known as lead compensator. As I told earlier, right, during the studying of the PD controllers, that the causal approximation of PD controller will be known as lead compensator. Now let's understand this in brief. So what is my controller transfer function of lead compensator? Controller transfer function of lead compensator, GC of S will be KDS plus KP, KDS plus KP. Okay, now like we have number of zeros more than number of poles. Here one of the zeros lie on the minus KD by KP. The location of 0 is minus KD upon minus KP upon KD. Okay, let me just put this one here. Okay, so like 1 0 is lying in this region. Sigma here 1 0, sorry, this is not a pole. Now what I wanted to do, what is a lead compensator? Well, the 0 is more near to the origin and the pole is further away from the 0. Like the pole comes after the 0, 0 comes first. So KP by KD. Now if I place a pole very far away from the origin, okay, very far away, okay, very far away, place a pole here. SP. Now my SP is much greater than SZ. 0 is much nearer than this pole. Okay, so then like what we want to do, we basically want to do the causal approximation, right? We don't want to mess up the root locus, we just want to do the causal approximation, because by placing a pole very far away from the origin, this won't affect anything. Okay, so this won't affect the system parameters as dominant, like this will be more dominant. Okay, so like this won't affect the dynamic performance of the PD controller, but this would make this controller attenuate. Okay, attenuate. So but what is the important difference here is this is a lead compensator, that is fine, this is a lead compensator, but if my poles and zeros are very near to each other, if here first I have a 0, then I have a pole, but they are very near to each other. Okay, SP and SZ are very near to each other. So if that is the case, let me check everything is recording or not. Yeah, if that is the case, if SP is very near SZ, then it will not be a causal approximation of the PD controller. It will be a lead compensator, but it will not be a causal approximation of PD controller. causal approximation of lead sorry, not causal approximation of PD controller. Okay, so this is the thing. So like here I have written the same thing, that all like approximation, all causal approximation, I should write causal approximation of PD controller, just all causal approximation of PD controller are lead compensators, but all lead compensators are not causal approximation of PD controller. So this is a lead compensator, okay, but this is not a causal approximation of the PD controller, and all causal approximation of PD controller are lead compensators. That is true because there will be one zero which is near to the origin and pole will be far away. This is all, that is also included in the lead compensator. So what is the important point is that this may come up in some EAC, like assertion and reasoning, those type of question, right? So yeah, just for theoretical knowledge you need to know, not much like this will come up in numerical stuff. Okay, first let's understand the difference with and without causal approximation of a simple PD controller. So here we have a PD controller and this is without the causal approximation. So for this, what will be the root locus? The root locus will be something like this. Okay, root locus will be something like this. So if you simply like find the breakaway point, breaking point, all those things, this you can do for yourself. Just pause the video, draw it and write the break in, breakaway point, value of k at the break in point. Okay, and what are the different things, how the root locus will look, okay, all these things, how many asymptotes it has, okay, virtual zeros, all those things. So you do it for yourself. I've already pre-calculated it. So next is with causal approximation. So now with causal approximation, like we had a 0 at s equals to 3, I added a pole at s equals to minus 3, I had a 0, I added a pole at s equals to minus 30. Okay, minus 30. Then what happens? Then basically it doesn't affect the DC again because it is added in time constant format. So here what happens is, if I'm within this region, right, if I'm within this region, this doesn't get affected. Okay, very far away my system gets affected, the poles differ from this, right? So yeah, if I am within this region, they won't get affected and my k will be varying within this region only. So obviously the performance like the transient performance, dynamic performance of the system won't be affected if I lie within this region. Just the system will become causal, and system will become realizable, because a single zero system can't be realized. Like where the number of zeros is more than number of poles, it can't be realized. Okay, you can calculate the break in point again. Okay, and then again breakaway point. So here you will get a break in as well as a breakaway point. You will get two valid points. So just keep in mind of that, and also find the value of k for this. Okay, so yeah, these are the things. So this is at s equals to minus 30. S equals to minus 30. Okay, s equals to minus 30 and this is s equals to minus 17, minus 12. Okay, so yeah, this is the breakaway point, and like you can calculate it for yourself. I'm not like doing the calculations now because that will just waste time. You will get two, like you just solve that equation. You write a of s equals to what? A of s equals to this numerator. Okay, a of s is this numerator, s plus 3, and what is your b of s plus 3. Let me just do s plus 3, and your b of s will be this denominator, a of s upon b of s, 1 plus a of s upon b of s. If you recall correctly, it is simply this s square into s by 30 into okay, and a dash of s equals to simply 1, and b dash of s equals to, like it will be two things, 2s into s by 30 plus 1 plus s square. Okay, fine, and this will be 1 by 30. So now like what you will do is you will equate this a of s into b dash of s minus a dash of s into b of s should be equals to 0. Okay, so this should be equals to 0, and if you equate this, you will get two values of s. Okay, you will get two values of s. One will be minus 7.5 and another one will be minus 12. Now both of them will be valid. Previously what used to happen was only one of them was valid, but both of them will be valid because both of them will lie in the root locus. You will see those are valid points in the root locus, so both of them will be valid. One will be break in point, so this will be the break in point and this will be the break away point. Okay, so yeah, this will be like this. So you can see here they are breaking away and they are breaking in. So if you lie within this range, then it won't matter much. Okay, so yeah, this is about with the causal approximation and without the causal approximation, what gets affected and what doesn't get affected. So with causal approximation, basically we can realize the system, we can make the system practical. Okay, so yeah, that is what is the main thing about this is. Now this is a one standard topic, like if some question comes from this, so you can solve this. So this is the standard circuit diagram of lead compensator. I will tell you how to remember this also. I will tell you how to remember this, but for now understand this is a standard circuit diagram. We obviously we won't study how it came, how it got derived. We won't study that, we don't have time for that. But if in the question this circuit diagram comes up and they tell you to find the maximum phase lead, okay, so you have to solve with that formula. Okay, how I will tell you how you will solve it. I will tell you. You don't need to remember that formula, like you don't remember the previous formula, or you don't need to remember any new formula here, but how to find the maximum phase rate of the circuit, because this is a lead compensator, hence the maximum phase rate will be like the previous case, that phi m will be equal to sine inverse 1 minus alpha by 1 plus alpha. Okay, so now how to write that, like how to, what is alpha, how to find that, so we'll all understand that. So if this is a lead compensators, then let's first check, is this really a lead compensator? So how to check that? So basically you convert this in the Laplace domain. So in the Laplace domain this will be R2 plus minus V naught of not t. We have converted this in the Laplace domain. This will be V naught of s and this will be V of s. Okay, so now let's write the transfer function of V naught upon Vi. So simply this is a simple voltage division. V naught will be Vi into this. If I consider this as Z1 and if I consider this as Z2, it will be simply Z2 upon Z1 plus N2. So it will be R2 upon, what is this totally? So this total is parallel combination of 1 by Cs into and R1. So it is R1 by 1 plus R1 Cs. So this will be R2 plus R1 divided by 1 plus R1 Cs. So now I can further simplify this, that my VO of S or VI of S is R2 into 1 plus R1 C of S R2 C of S plus R1. Okay, so this is the thing. Now what you can do is you can convert this in the standard format. How to convert this in standard format? So what was our standard transfer function? If you recall correctly, standard lead compensator transfer function, if I just copy this one up, where did it go? Yeah, it was here, right? Yeah. So these are standard transfer function. Yeah, sorry, actually some delivery boy came at the door, that's why I had to pause this recording again. So let's restart. I was at this stage that we have to compare these two equations. So basically what we'll do is we have to compare these two, right? And so I have to convert into this format. So the coefficient of this is 1, coefficient of s is 1. So here the coefficient of s is r1c, so I have to take common r1c, and from here also I have to take something common. So we'll see. So first this will be r2, and I will take common r1c over here, 1 by r1c plus s divided by r2, and this I can write I can take this inside, so this will be r2 plus r1 r2 cs plus r1. So this will be equals to, if I take common r2 r1 c into s plus 1 by r1, sorry, 1 by r1c s, I can take common c r1 r2. So if I take common c r1 r2, this will get cancelled, right? This will get cancelled, so kc will become 1 only. So if I take common c r1, this will be s plus r1 plus r2 divided by r1 plus r2 divided by r1 r2. Okay, so yeah, c r1 r2. So now what I can do is, like, now I can compare with these two, right? These two. So this here kc will be 1, kc will be 1, kc will be 1. Okay, and tau will be r1c, tau will be r1c, and this r1 plus r2 divided by c r1 r2 is equals to 1 by alpha tau. So 1 by alpha tau equals to r1 plus r2 divided by c r1 r2. Okay, so this alpha 1 by tau is equals to this r1 c, so r1 c will get cancelled, r2 will be present, so alpha equals to r2 by r1 plus r2 simply. So here my alpha, what I can see is obviously this r1 plus r2 will be greater than r2, so alpha will be less than 1, alpha will be less than 1. Okay, so my alpha will be less than 1. So now how to remember this? So if you want to remember this, first thing is you have to identify whether this is a lead compensator or not. How you can identify, I will show you just within a minute. But how to remember the value of alpha? If this is a standard lead compensator circuit, then you can compare with this transfer function of the lead compensator, and also you know the standard formula for the maximum phase of a lead compensator. What is it? It is phi m equals to sine inverse 1 minus alpha divided by 1 plus alpha. So that you can remember, but if you find the value of alpha, you can find the maximum phase. So how to remember the alpha? So alpha will always be less than 1 for a lead compensator. So what will be in the numerator? Numerator will be the resistor nearest to the output, R2, and what will be in the denominator? The resistor of these two, R1 plus R2. Okay, so R1 plus R2, R2 by R1 plus R2. So that is about the alpha. Now what is the next thing? So next thing is like, if they ask you to find the value of that tau, or not tau, sorry, the frequency at which the maximum phase occurs. So that will be what? 1 by tau into under root alpha, basically the multiplication of gm of these two poles, gm of these two roots. So how to remember this? Tau is tau of this r1c, that is recalled, and alpha already I told you how to remember. So yeah, that is how you can remember this formula. Now let's understand how to remember like how to understand that whether this is a lead compensator or not. How do we understand that? So all this I told you, right? This is for the standard lead compensator circuit. If some circuit other than this comes up, we have to derive, or sometimes what helps is we have to check the options. The options can help us eliminate few things. That is also very important. Okay, so yeah, that is one thing. Now, how to identify whether this is a lead compensator or not? So what is a lead compensator? Where the zero is near to the origin and pole is further away from the origin. So it will act like a high pass filter. Zero comes first, then pole comes. Hence, in the border plot, first we get a plus 20 dB per decade slope, then the slope becomes zero. Okay. So for low frequency region, low frequency region, my how will my circuit look like? So for low frequency region, my S is 0. If my S is 0, 1 by CS will be infinity. Hence this will be open circuit and this will be in series. So I can replace my circuit like this. Okay, I can just copy this. This will open circuit. So basically my V of S equals to V of S into R2 by R1 plus R2. Okay, so V of S will be this VI of S into R2 by R1 plus R2. So yeah, this is this thing. So for S is 0 for low frequency region, the ratio would be something like this, which is, so what I want to say, VO upon VI equals to R2 by R1 plus R2, which is not equals to 0. So which is something less than 1, right? Which is something less than 1, because this will be something less than 1. So we are getting low gain in the low frequency region, and in the high frequency region what is happening? Let's see. In the high frequency region, S is infinity. So if S is infinity, so here this is S is 0, DC gain basically, and if S is infinity, what will happen? 1 by CS, S is infinity, it will go 0. It will go 0. Hence the impedance is 0. Hence this will become short circuit instead of open circuit. So here, so this will get short circuit. So R1 is not of any use. R1 is not of any use. So this is only R2. And this is VO, and this is VI. Okay, so VO upon VI, this is R2. So output voltage will be directly equals to input voltage, because this is directly connected across this, right? So VO will be equals to VI. So here what do I see? VO by VI equals to 1. Okay, so which is more, like more than the previous case. So here it is acting like a high pass filter, because at high frequencies we have more gain than the low frequency gain. So this is acting like a high pass filter, because high frequency gain more than low frequency gain. Low frequency gain. So like this will be the end of this lecture, because we have explained the lead compensator and it has been more than 1 hour. So I have explained in detail what a lead compensator is and how to derive it basically. Okay, so like in the next lecture we'll learn about the lag compensators and lag lead and lead lag compensators. Okay, so yeah, you can like do a basic revision, and then we'll start in the next lecture. Thank you for watching, and I will see you in the next video.